Good evening, everybody, and welcome once again to yet another IT Masters free university short course. We will be kicking off, as always, in about 3 or 4 minutes while everybody crams into the room. While we're here, please introduce yourself on the webinar chat. Tell us where you're hailing from, what the weather's like, what's going on in your life over there, anything you want to chat about, and we will, as always, just be back in about 2 minutes when everybody's in. Just bear with us for a second or so that we're ready for the YouTube. Okay, welcome once again to the Networking Certifications Essential Free University Short Course from IT Masters, presented in conjunction with Charles Sturt University here in Australia. Thanks for joining us for the first webinar. It's a new course. We're very excited about it. My name's Shane Murphy. I'll be hosting for this evening, and your mentor, Iain Robertson, is coming along shortly. He is one of our more recent mentors, but you may well have encountered him if you've done any of our other courses or last year in our Networking Essentials course. I think Next Gen Security course. That's what we were doing. Wherever you're watching this, we hope that you are safe and well and content, relaxed in your chair, got a cup of tea or a drink or a snack in hand so you can get in for some good content. Before we begin, as always, a little bit of housekeeping. All the webinars for this course will be held at 7:30 p.m. Australian Eastern Daylight Savings Time. That's Sydney time. If you miss one or more, don't worry. We do make the recordings. The recordings will be available tomorrow, the day after the session is live. Despite the recordings, we do like it if you can actually come along because, we get a lot of interaction with everybody chatting amongst themselves and asking questions, and it really makes it better for everybody, including the people who do happen to watch it later if they've missed out. We obviously use Zoom for our webinars, and we encourage you to ask questions and the use of the chat, of course. We ask that you direct all of your questions that you want Iain to answer to the Q&A section. That's down the bottom of the screen. You can just click on Q&A and you'll be able to type in your questions there. We will answer as many of those as we possibly can. Sometimes we get a couple of hundred, sometimes we get 50. We can generally answer about 30 to 40. If it's a question about general things about IT Masters or short courses in general, just put them in the chat and Kit will get around to doing them. Kit is our short course master, looks after our learn.itmasters.edu.au website and really keeps a whole tight handle on everything. So welcome to Kit and thank you very much for coming along. Often you will find in the chat, by the way, that there are people who actually know probably more than we do about our subjects, and they will come back to you with answers if you do have different questions along the way. We have quite a few people that tend to come to quite a number of these. For those of you, though, who have never taken part of our short courses, welcome, first of all. IT Masters is a training organisation, and we exist primarily as a partner to Charles Sturt University, who is a regional university here in Australia based in country New South Wales. We do only 100% online masters and graduate certificate courses, and we work to create, and deliver them in a way that is relevant and pertinent to people's real life experience. So they do have some academic content and they have content delivered by people such as Iain who work in the industry every day. We like to do these short courses because we think that they're a great way to introduce you to online learning and, gets you, particularly if you haven't studied before, gets you used to the way that we do things. Also, hopefully if we do a good enough course, you might be encouraged to enroll in one of our master's courses because a lot of the same subject matter is coming up in the short courses as in our actual subjects. Anyway, with that said, though, we want this course to be a useful and rewarding exercise. We want you to learn some interesting info, have a bit of fun, make some connections, maybe with some of your fellow students. To date, over 3,000 people have enrolled in this course, so get busy here and remember about the forums at learn.itmasters.edu.au. There's lots of forums there. You can chat amongst yourselves about all sorts of stuff in those forums, and every now and again we do check in and answer some questions. As I said, Kit is around tonight to do the support and the moderation of the chat. If you've got any questions around, logins, usernames, emails, all that sort of stuff, either send them to Kit or send them to info@itmasters.edu.au, where they'll be answered by either Kit or Lil in the next day or so. It's time, though, for me to shut up and welcome Iain. Iain is as I said, a little bit new to ITM. He's been here for about, I think, a year now, as opposed to some of our mentors have been here for nearly 20 now, or 15 or something. He's a vastly experienced industry practitioner. He has so many certs and qualifications that you would not believe. He's good on the yarn, I'm told, and we're looking forward to this short course from him as we hear nothing but great things from his regular students. Please make him welcome. How are you, Iain?
Not too bad at all, Shane. Thank you very much for the intro. Um, Looking forward to delivering this course.
Yes, I suppose we should actually just address the little pink elephant in the room. And why did we change the course name? As many of you will know, we started out at this as CCNA version 4, and we're now calling it Networking Certification Essentials.
Yeah, it's a good question, and it certainly has raised a few questions and eyebrows I've seen in the forum so far. The main reason is that the feeling was that doing a Cisco specific course, when obviously there is far more to networking than just Cisco, was absolutely relevant. Does that make the material less relevant to Cisco? No, it doesn't. The reason being is that the amount of study and work that you would need to put into completing a CCNA anyway far exceeds the roughly 4 hours worth of tutorial time that we'll have over the next 4 weeks. That in turn means that regardless of which path you take, as a student, you're going to need to spend quite a bit more time doing study. So that's true whether you're doing CCNA, the Cisco certification, the JC, the JNCIA, which is the Juniper equivalent, or Networking Plus, which is an industry neutral course that I'm sure Shane would love to talk a little bit more about. The long and the short of it, though, is this material is just as relevant to the CCNA as to the others. But if we were to do a Cisco specific version, the reverse wouldn't necessarily be as true.
Also, I guess, as you said, there's a lot more. This covers probably a quarter or something of the course of
Yeah,
CCNA in general. So there's a lot
that's
more work
correct.
to be done. And
Absolutely. There's a lot of study that's needed to get through any of these courses. This is designed to sort of act as a flying start on your journey towards those certifications.
I will take this opportunity, since you've battered that ball up in the air, to remind everybody about CompTIA certifications. We've recently been offering a couple of those. Network Plus is one of the ones that we will now be offering as well. In fact, we have about a dozen, I think, all up, certifications and exam vouchers for the CompTIA library. And because, as you said, Iain, this covers, this is suitable for Network Plus as well as other things. For people who pass this course, they will be eligible for up to 15% discount on the CompTIA Network product set, or 5% just for enrolling if you don't actually go through and do the exam. So, we try and make it useful for people as well as anything else. And, in the future, there are discussions underway that maybe we can offer some of the Cisco product line at some point in the future as well. Anyway, that is more than enough from me for this time. We'll check back in with questions along the way. So over to you, Iain.
Yeah, no worries. So yeah, just to reinforce though, this material is very heavily based on a Charles Sturt Uni IT Masters subject, ITE 526, which is practical internetworking. And so with that in mind, doing this will give you a good taster of the kind of material that you're going to see in a university level subject as well. So a little bit about me. Obviously, Shane's done a very good job of introducing me, probably better than I deserve, dare I say. But long and the short of it is, I've got over 25 years of experience working in and around the IT industry, and particularly on networking and networking space, service provider, large research networks, that sort of thing. I've done a couple of IT Masters degrees myself, and I'm currently actively working through yet another one. But I guess the key thing here is that everybody that attends this has the opportunity to bring something to the table. Everybody here knows something that somebody else does not. So please leverage that. Please use that, because teaching is a big part of learning as well. Obviously, we've covered the class times and so on already. These slides are shared as part of the material as a PDF. And that's important because there is actually supporting information towards the back of this deck that we simply will not have time to go through, but that is valuable for your further learning. Shane's obviously also already covered how we're going to contact people and the best ways to get in contact with us. In terms of Q&A, the best way to ask questions that you want answered live is through the Q&A panel. The best way to answer questions that your peers might, or ask questions that your peers might be able to answer, is through the public chat. So what is this subject? So first and foremost, it is an introduction to networking. It is entry level. It is designed to give you a taster of the kinds of information that you will need to be aware of in order to pass any of the certifications mentioned here. So be it the CCNA, the JNCIA, which is the Juniper Network's equivalent of the Cisco cert, or the CompTIA Network Plus cert, which has also been mentioned. Now, we'll touch on it a little bit, but you may be aware that particularly the CCNA and JNCIA actually come in different flavors, different streams. This is very much focused on the routing and switching stream for those that are familiar with such things. Now, there are some lab type capabilities available on the internet. The best way of going with this, if you choose to build your own lab, is to look for tools like GNS3. And I'm more than happy to put up in the forums later some pointers on where to go to achieve such things. And in terms of study tips, the best tip I can give is to read, reread, and ask yourself, test yourself lots of times, test your knowledge until you're sick of testing your own knowledge. And if you do have access to labs, a good way to do that is to actually build infrastructure and basically tinker with it, play with it, figure out how things actually work in the real world. In terms of where this fits in, so in terms of the CCNA, it is broadly modeled on the CCNA RNS, routing and switching model. So that is, we're not going to be talking much about service provider or security or wireless. We're going to be focused on what in the parlance of networking is really layer 2 and layer 3. Similarly, JNCIA wise, we're looking at the Junos equivalent, the routing and switching stack, as it were. The other certs are absolutely worth looking at, but they're certainly outside the scope of this particular set of topics. And then, of course, there's Network Plus, which is, in my view, just as valuable as CCNA and JNCIA, and indeed arguably can be more valuable for the simple fact that it is much more vendor neutral. Obviously, Cisco, Juniper, other vendors, their certifications are built around their products, and that's for very good reason. Whereas Network Plus is designed to give you a far broader understanding of the networking industry and networking standards in general. And to me, that is very, very valuable. That's not, however, to deprecate the value of any of these associate level industry certs, vendor certs. They are absolutely, absolutely valuable in their own right as well. Just touching on online labs again, there's plenty of different options online. Best thing you can do is do a quick Google search for them. If you've got the wherewithal to do so, it's always worth trawling places like eBay, Gumtree, Trade Me if you're in New Zealand, etc. Looking for secondhand, maybe out of support hardware that will run the operating systems that you're interested in. If you've got that wherewithal, I find that is a very, very effective way to learn the basics. Then there's a tool called GNS3, which provides a software emulation of a range of different networking hardware and basically allows you to build up simulated networks of various sizes and shapes. There's a few different links there. Obviously, these will be shared in the PDF as well. Now, there is a suggested textbook It is absolutely not not required, but it is absolutely recommended as a good guide, especially if you're going down the path of the CCNA specifically. Now, I guess before I move on, Shane, is there any questions that need to be addressed at this point?
Um, Look, there's a lot of questions about certificates and stuff, so let's just make that clear right up front. The certificate that we issue at the end of the course and by the way, that's contingent upon you passing each of the weekly quizzes and the final exam, is a certificate from IT Masters / Charles Sturt University. It is not the equivalent of CCNA. It just says that you've done some prep for CCNA or some of the other certificates. So just want to make that absolutely clear. But it is a certificate that is well liked. We see lots of people sharing them on LinkedIn all the time. So, and 3 of them does qualify you for a subject credit in one of our paid courses. Having said that, Tan has asked, which is better, CompTIA Network Plus or CCNA?
So I think in some ways I answered that. They're all very valuable. If you were working or if you're focused on working in an industry or in an organization that uses a specific vendor, then of course a vendor certification is going to be valuable because it focuses on the specifics relevant to that vendor. Um, if you are just starting out, let's say you're very early in your IT career, you want a better understanding of how networking in general works, then you really can't go past the likes of the CompTIA Network Plus cert. It gives you a good, solid industry basis and standards basis of knowledge that is equally applicable whether you're dealing with Cisco 10, Juniper 10, Hewlett Packard, or any of the other multitude of network vendors that are out there in the industry.
Great. I'll ask you one more question and then there are a lot of people asking about GNS3, but we'll worry about that later on.
Yeah, I'll answer questions about GNS3 in the forums later.
Yeah. Kit's already typing an answer to this, but we've got somebody already asking about the final exam and a practical component. There are a few practical component type questions at the moment. Is there anything you want to talk about that?
Yeah, so the final exam is predominantly multi-choice. So it is predominantly based on the material that's covered in these slides. You do have to apply some logic and some applied knowledge to that. It's not simply rote. It is, however, of course, open book as it would need to be. But no, there is not a fingers on keyboard lab type component, regrettably. I'd love to be able to do that, but unfortunately it is outside the scope of what can reasonably be done within the systems that we have here.
Great. Let's plow on.
Excellent. All right, so this is week 1. Similar to the way networks are constructed, and we'll obviously talk about this over the next several weeks. We're going to be working from layer 1 upwards, essentially. We're going to be working from the physical layer up through layers 2 and 3 and beyond, because fundamentally, and there's a good reason why most networking courses approach it this way, that's the way you would typically approach troubleshooting as well. So with this, we're going to be talking about network fundamentals. We're going to be talking about the OSI stack, as it's called. So the OSI and TCP IP models that represent the way networks are constructed. We're going to be looking at the difference between TCP and UDP, and I was quite amused to see in the forums already some old classics in terms of jokes regarding TCP and UDP. We'll be talking about different kinds of hardware. We're going to be talking about different architectures in a broad sense, and we'll also be talking about networking. That is to say, network subnetting. So we'll start first of all with what's called the OSI model. So the OSI model is a 7-layer model that is designed to broadly represent the way a network. Now, this doesn't necessarily mean a modern network. The OSI reference model is a very old model, but essentially it's designed to represent how that network is constructed. So essentially, you can think of it as a layer cake, if you will. Essentially, there's 7 layers. Each layer is necessarily built on and depends upon the layer underneath it. So essentially, though, it looks broadly like this on the sort of middle to left part of the screen. We have at the bottom a physical layer, the physical layer being obviously the wires, the electrical or optical connectivity between devices. Data link, which provides the actual signaling, the converting electrons into bits, if you will, or photons into bits. We've got the network layer. This is what we would typically call layer 3, which actually provides the connectivity from end to end across the network. We've got the transport layer, which provides the end-to-end application level communication for a platform or for a set of systems. We've got what's called the session layer. Session layer provides a higher level of inter-system communication, provides a level of what we're going to call session persistence to allow for communication to occur. The presentation layer provides for encryption and more enhanced forms of data presentation. And then, of course, there's the application layer, which is essentially the business logic, the business layer. Now, obviously, compare and contrast that with what is on the right. We have the TCP model, which basically broadly breaks that up into 4 sections. Network access, which consists of layer 1 and 2. The internet layer, which is layer 3. The transport layer. Now in TCP/IP, that's actually TCP right there. That's the bit that provides for end-to-end connectivity from an application, say your web browser to a web server. And then you've got the application itself, which is typically the data that's carried to your web browser. So that's the OSI model. Those 7 layers will often be represented in pretty much every certification exam you might ever look at. And it's really important to understand which layers fit in where. So physical, data link, network, transport, session, presentation, and application. That's the typical way in which it'll be looked at, sort of from bottom to top. And it's important to understand that every layer relies entirely on the layer below it, and every layer provides entirely to the layer above it as well. In terms of where the various applications fit in, so at the bottom in the network interface, TCP/IP model, or the physical and data link, you typically have Ethernet. Now, some of you will know that there are other protocols and technologies to provide connectivity. Ethernet is just one of them. But for these purposes, it's safe to look at Ethernet as the key here. Now, Ethernet can be a piece of Cat5 or Cat6 copper cabling. It can be a fiber optic connection. It can be, after a manner of speaking, your wireless link as well. Then on top of that, you have IP. You've got your that's the Internet Protocol, the IP part of TCP/IP. So it provides for the baseline connectivity between 2 hosts. And on top of that, there are some base services that are always needed. So there's a service called ARP, which is the Address Resolution Protocol, which is designed to allow 2 hosts to find each other using data link or layer 2 services, but do so at layer 3 using IP. There's ICMP, the Internet Control Messaging Protocol, which is designed to allow, among other things, the ping command to work, but also to allow signaling between devices. So if a device can't receive a certain type of traffic, ICMP is one mechanism it can use to do that. And then there's another protocol which is associated with multicast called IGMP that also lives at this layer. Above IP, you have TCP and UDP. So you've got a transport communications protocol, and you've got a user datagram protocol. Those 2 protocols provide different classes and types of service to applications. So typically a web browser uses TCP. TCP is designed as a session-based protocol. So essentially, while a data flow is made up of individual packets of data, TCP assembles those into a stream. But essentially, think of it like a telephone conversation. You pick up the phone, you dial a number, you talk to them. And when you're finished, you hang up. while you've got that open, you've got a session between you and the party you're calling. UDP is much more like the postal service. It uses datagrams. It basically sends individual packets of data with no guarantee that they'll be received or be received in a particular order. And then sitting on top of all of these, you've got different application level protocols. You've got HTTP, which is essentially web traffic. You've got Telnet, which is an older form of remote access to servers. You've got DHCP, which allows for devices to get IP addresses off the network. And you've got ping, which is, of course, as I said, based on ICMP. Now, up and down the stack, you've got different levels of encapsulation and decapsulation. So an application will typically create a chunk of data, call it a datagram. That'll get a TCP header or a UDP header added to it as it moves down the stack. That will then get an IP header added to it that indicates the destination that the traffic's got to go to. And then beyond that, to know how to contact the next segment on the network, there is a layer 2 header, which basically gives the MAC address, which is the physical address of a device that is immediately and directly connected to this particular device. When we get to the other end, once this has traveled as bits on the wire to wherever it's going, the reverse process takes place. So the network card will typically strip off the first few sections. Then the operating system takes care of the rest until the only thing the application has to care about is the data that it's asked for in the first place. Before I move on into hardware devices themselves, how are we going for questions?
Not too many. They were all about GNS3, which we will ignore.
Yep.
Can Cisco Packet Tracer be used?
In the online labs?
Hmm.
Look, quite possibly. Quite possibly. That's probably a bit more advanced. I'd be inclined, and again, I'll probably treat that in the same way as GNS. I'll put some tips and pointers up on the forums afterwards, because it
Right.
is a bit more nuanced than I can sort of give in a 2-minute answer, as it were.
Okay. From Mr. AA, I often get confused when their protocols have been accepted on the firewall. However, a packet is dropped due to the three-way handshake. Am I understanding that there could be a network issue?
Absolutely, yes. So the three-way handshake, I'll just skip back a slide actually. So the three-way handshake is a construct of TCP, and essentially it consists of a client device sending a message to a server that essentially says, "Are you there?" The server then responds with, "Yes, are you there?" And then the client responds a third time with, "Yes, I'm here." In other words, that three-way handshake basically allows the two devices to absolutely confirm the other's ability to accept data and communicate successfully. Now that's done to make TCP what's called reliable in networking parlance. There are trade-offs to doing that. Obviously, there's a lot more overhead. It means that TCP is a lot more prone to loss of data, particularly when it comes to particular types of firewalls. And there are many reasons why a TCP session might not start. It can, and many of them do come down to, problems with lower parts of the network. So it can be a routing issue somewhere else in the network. It can be a switching issue. It can be something as simple as having a misconfigured network card.
I'm assuming this is a joke. What type of FEC does UDP have? Lol.
What type of forward error correction does UDP have?
I'm
Virtually
assuming
none.
zero.
Yeah, virtually none is the correct answer. UDP doesn't provide any guarantees in and of itself of data's ability to get from A to B. And in fact, it's designed specifically with that in mind. So it essentially shoves the problem of reliability up a layer to the application. If the application particularly cares about reliability, then it's up to the application to decide how to handle it. And maybe one of the things it will do is apply a form of forward error correction to its own data. We move forward again to the slide, If it wants to use forward error correction, it might do so at this layer.
It's very much horses for courses, isn't it? I came from a IoT background where we were measuring traffic in bits rather than nowadays where things are being measured in megabits and
Yeah.
megabytes.
Well, it's also, I mean, networking generally, the expected error rate on a network link has dropped orders of magnitude since I first got into the industry. So, fiber optic connections, you might expect to have an error, it one in, several hundred trillion bits. So the likelihood of a bit error, which is what forward error correction would typically adjust for, is practically zero. And given on ultra high speed links, 100 gigabit Ethernet, 400 gigabit Ethernet, and beyond, the protocol itself, the IEEE standard for those interface types, actually includes forward error correction as a part of the standard. So it actually ends up getting done down here. So there's even less reason for UDP to worry about it.
Yeah.
UDP would typically, so for those who are wondering why on earth we'd use UDP when TCP is designed for reliability, voice traffic is the common answer, or
And
indeed Zoom.
and also, low volume stuff we used to find with UDP versus TCP over mobile networks, the traffic required for TCP was 10 to 100 times the amount of traffic required for
Yeah,
UDP. And if you're paying by the bit, you want to know.
absolutely. And that's the thing, that same fact that TCP requires a session to be set up each time means that all of that traffic's got to be transferred over the network as well. But certainly voice networks will always use UDP because while voice doesn't want any delay, and obviously UDP is great if you do not want delay, um, it can cope with the occasional loss of a packet here or there. You've all had the encounter of a mobile phone that gets a little bit blocky from time to time. The audio quality drops and then comes back. That can be thought of as what happens when you lose a single packet or a couple of packets from a UDP flow or a UDP stream.
Which sort of answers Hanny's question, which is how do you know if a UDP session is established? I think by definition, there isn't really a session
Yeah,
established.
you don't. In fact, troubleshooting UDP is probably worthy of a 12-week class in itself, to be very honest, because it is very difficult. Compared to TCP in particular, typically involves a lot of packet captures and trying to tap various parts of the network and so on. But yeah, the long and the short of it is you don't. The only real arbiter of whether the data got there is whether the client at the other end actually has something to work with.
One more question. Wouldn't there be verification of data prior to de-encapsulation to ensure the destination is the right one where data is sent? Assuming that's down to the application.
Yeah, look, nothing in the TCP, UDP, or even Ethernet standards requires that. And in fact, it's one of the reasons that meddler in the middle attacks, formerly known as man in the middle attacks, are such a problem. It's very, very easy to fake or spoof any of these headers, any of the ones you see on the screen, and make a particular packet look like it comes from somewhere else. The way applications will typically deal with that is through the use of encryption and hashing. So they'll sign each packet, each payload. They'll digitally sign it so that on the one hand, you know where it's come from, and on the other hand, you know whether it's been altered in transit as well. But again, I mean, you could spend and indeed, there is an entire subject dedicated to cryptography within the IT Masters CSU world.
One last question before we move on. Adil has been asking a couple of times, why OSI and TCP when both serve the same purpose?
That is an excellent and very insightful question. I love it. Um, so the main reason is that TCP is only one of a multitude of protocols that exist now and have existed in the past. TCP is obviously the model that we use today, and it works pretty well for both IPv4 and the newer IPv6 that we will be talking about in more detail tonight. But there are other protocols. Some of you of a certain vintage may be familiar with a protocol called IPX, the Internet Network Packet Exchange, and its sibling, the SPX, which were very, very common in the early 90s when dealing with Novell NetWare networks. Now, some of you may never have even heard of Novell because as a company, it hasn't really been at the forefront of people's minds for, well, at least 15 years or more. But IPX SPX uses a very different stack representation that far more closely represents the OSI model. Then you've got routing protocols like ISIS, the intermediate system to intermediate system routing protocol, which is very common in service provider networks. That uses a very strict OSI-like model for representing computers and routers within a given network.
Yes, TB has said NetWare straight up as soon as you were talking about that.
Yeah. Oh well, that's yeah. NetWare's the canonical example. IPX SPX has, as far as enterprise has been concerned, has been around a lot longer than TCP UDP. Now, obviously, TCP IP and UDP, they come out, for those that want a little bit of history, they both come out of DARPA, which is essentially the US government, the US military, whereas IPX and other protocols like Banyan Vines and so on were essentially industry-led. Now, ultimately, for various good reasons, TCP IP won, most importantly being that it's, vendor neutral, where the others had royalties to pay to various people. But knowing the OSI stack, knowing how the how the logical representation of these datagrams and these data flows goes is still a very valuable thing and is absolutely covered in any of the exams that I've mentioned so far.
Okay, let's hang on.
Yep, cool, awesome. So now we'll just move on to a little bit of hardware and a little bit of hardware history. And again, if I'm mentioning this, if I'm showing any of this material, it is because you will find it in any of the exams I've mentioned. You might not expect to see a hub in the real world, in a typical industry or corporate environment these days, but you can and do see hub-like behavior from switches, and I'll explain what I mean in a little while. So it's well worth looking at the difference between the three types of devices. And you'll see there's a sub bullet point under routers, and I'll get to that as well, because there's a lot of blurred lines here between these different devices. You can get switches that behave like hubs, and you can force any switch to behave like a hub if you try hard enough. You can get switches that behave like routers. You can get routers with enough ports that essentially makes them a switch. So we'll talk about that, and we'll talk about why we still have hubs in there as a comparison, even though the last time I personally used a hub in a corporate network was 1998. So hubs, as I said, you're not going to see them that often in the real world unless something is very, very wrong. Essentially, and we'll talk a bit about what broadcast and collision domains means, but essentially they're a device that just acts as an electrical connection between two or more devices. They've got a single broadcast domain, and what I mean by broadcast domain is that they're a party line. Everything hears everything said by everybody else all at once. And if you've ever been in a really noisy room full of people all trying to talk to each other, you know straight away how hard that can be. And it's even harder when computers don't like electrical noise. And any signal they're not interested in is by definition noise. What that leads to is the very next thing, which is a single collision domain. Now, a collision in these terms doesn't mean, physical crashes and damage to devices. What it means is that two devices have tried to talk at the same time and have drowned each other out. So nobody gets to talk to anybody. So Ethernet has a bunch of mechanisms to deal with this that fortunately we don't generally need to deal with all that often. But it's important to understand this because, as I've already alluded to, there are ways to make a switch behave like a hub. Various forms of denial of service attack will do exactly that. For example, you can make a switch think that there are more devices connected to it than it has memory to cope with. And the net effect of that is that it will resort to being a hub to try to allow whatever is out there to try and talk. Not generally a good outcome for anybody involved. There are also various software defects and other forms of bug that can cause broadly the same behavior. Never great when it happens, but it's great to understand what's going on when it does occur. Now, from an OSI perspective, a hub is considered a layer 1 device because, as I said, they're essentially an electrical connection from, one device to at least one other device. And when I mentioned party line, for those that aren't familiar with the concept, back in the earlier days of copper telephony, where you had a landline at home, if you lived in certain rural areas, when you picked up the phone, there was a better than even chance that you'd probably be listening in on somebody else's conversation, such as one of your neighbors. And that was simply because the way the telecommunications providers saved money, particularly in low density rural areas, was essentially to run a single service line to all consumers. Now, you might have your own phone number and only your phone would ring when it did. But if you happen to pick up the phone when someone else happened to be using it, you'd have a live service. You'd be able to listen to what they were saying and vice versa. Not great. Luckily, we don't deal with that anymore. But that's what I mean by party line, and that's essentially the way a hub works. Now, switches these days, this is normal. Now, in industry and specifically standards parlance, so IEEE parlance, a switch is often referred to as a bridge. So for the purposes of the exams, the two terms can be deemed to be synonymous. Historically, bridges were slightly different devices, particularly in the context of hubs. Typically, a bridge was designed to connect at layer 1 and 2 hubs together and eliminate the collision domain between the two. But that's essentially what a switch does anyway. So what a switch does is it provides a single broadcast domain. And what that means is that you have the ability to send a packet, that is a piece of data, that every device on that switch can receive all at once. And that's at layer 2. Now, what the difference is, though, is that we've potentially, particularly on a modern switch, essentially eliminated collision domains altogether. Or more accurately, we have one collision domain per device on the network. That is, a device can send data and receive data at the same time because they've moved from a simplex model where everybody talks and hears at once to a duplex model where a device has a separate channel for transmitting and a separate channel for receiving. Now, that in turn helps make them a layer 2 device. They still work at layer 1, they have to, but they now have the smarts to understand things like MAC addresses and other constructs that exist at layer 2. That then gets us very neatly into layer 3. Layer 3 and routers, well, layer 3 is routing. That's so to back up a little bit. Switching is typically what you do at, say, the building level or at home, for example. You might have a switch connected to your computer at home. You might have a printer and maybe a couple of other devices connected to the back of that switch. And then hanging off one side of that switch will be a router connecting you to the internet. Now, if you've got a single ADSL modem that's got 5 ports on the back of it, that is a combination of a router in the form of the interface to the internet, essentially, and a switch, which is the interface to all of the devices within your network. There is a concept, particularly in Cisco land, called a layer 3 switch. A layer 3 switch is a router. It's a device that's capable of connecting multiple layer 2 networks together and providing connectivity between them, while eliminating any form of broadcast or collision domain, and also allowing multiple layer 2 devices, so multiple PCs, for example, to talk to each other. They're also known, particularly in Cisco's exam terminology, as a multi-layer switch. The big difference, and you'll see this in the CCNA, between a router and a multi-layer switch or a layer 3 switch is that routers have fewer ports. Typically, particularly in service provider land, a dedicated router might have maybe a dozen ports, whereas it's not uncommon for a multi-layer switch to have, 24, 48, or even more data ports on the front of it. And that reflects their use case. Typically, a switch, even a large multi-layer switch, will be designed to connect to very potentially hundreds of computers, printers, servers, whatever it might be, wireless access points, you name it. Whereas routers only have to connect to another couple of switches, and generally that's about it. So before I move on to physical media and so on, any questions?
Okay, Stephen asks, there's been a lot of talk recently about network slicing in 5G networks, which provides users a dedicated mini network within a larger network, if they're willing to pay for higher availability and reliability. What layer of the OSI model is slicing done at?
That is an excellent question, and I'm going to answer it, but I'm also going to say it is very strictly outside the scope of this particular course because that gets very much into service provider land. Now, network slicing actually sits at multiple layers within the network. Obviously, layer 1 and 2 from an OSI perspective are still what they are within a mobile network. They are the wireless infrastructure, the RAN, the radio network, and so on. The slices generally sit from layer 3 upwards, but, and there is a big but here. There are a range of technologies. Slicing is one of them. MPLS, multi-protocol label switching, is another, which allow you to represent layer 2, that is device to device, simplified Ethernet type connections over very long distances and indeed over a network that is otherwise layer 3. So generally speaking, they're represented as being layer 3 upwards, but there's a common interpretation of MPLS that it kind of exists at layer 2.5, and the same is broadly true for slicing.
Is slicing similar to the use of APNs in mobile networks, etc.?
APNs are another representation of part of slicing, yes. There's also a little bit of an overlap conceptually with concepts like VLANs, which I do cover a little bit more very soon.
Right.
Essentially, though, slicing APNs, VLANs, SSIDs, when you're talking wireless networks, etc., they're all ways to isolate or compartmentalize a network and provide virtual infrastructure to a subset of users.
Nick's just asked what an APN is. It's an access point node. It's a technical
Yeah,
term.
yeah.
Mobile
So
phone network.
yeah, that's the one.
What makes a bridge different than a hub and a switch? What are the uses of bridges these days?
So these days, a bridge and particularly from the point of view of the standards. So when you look at, say, the spanning tree standard, for example, or TRIL, which is transparent interconnections of lots of links, which is a standard designed to prevent loops on networks, they use the term bridge interchangeably with the word switch. So for those purposes, there is no difference. Historically, what a bridge did was it acted as a layer 2 connection between two hubs that also limited the collision domain to a hub by hub basis. So essentially, it acted like a two-port switch. It allowed two hubs which had their own collision domains to do their thing and not interfere with each other. Getting towards sort of the theoretical a little bit, but there's a fundamental limit to the number of devices that you can connect to a hubbed network before they will basically drown each other out and no reasonable amount of data will ever pass through that network. And broadly speaking, that number is around 30 devices. I'm saying broadly speaking because anybody with a good background on networking will know there are exceptions to what I've just said. But for the purposes of this discussion, 30 devices in a hub-based network is about the upper limit of what you can reasonably expect to squeeze out before performance is, crippled. Back in the day, and I'm talking up to probably the mid-90s, switches were really expensive devices, and the vast majority of organizations just could not justify the cost, if indeed they had hubs or switches at all, and didn't just have thin net, that is coaxial cable running from computer to computer to computer, all in one big daisy chain. Now, that said, if you can only cope with 30 computers at a time, say a large school classroom worth of computers, then if you've got a large school, for example, you're going to be in a world of hurt. That's where bridges come in. They allow you to have a relatively simple way of interconnecting these hubs, allowing them to talk with each other and allowing traffic from one computer to talk to another computer in a different part of the building, without having the contingent effects of having 60, 90, 120 computers all in the same collision domain. That is, all shouting at each other and drowning each other out with every single piece of traffic they try to send.
Would a stack of switches be one broadcast domain or one each?
So a stack of switches. So I'm going to use one of my favorite terms that everyone's going to hear many times in the next 4 weeks. It depends. So assuming they're all configured with a single virtual local area network, a single VLAN, then a stack is essentially one switch and would be considered to be a single, I'll go back to this for you. There'll be a single broadcast domain with one collision domain per device connected to that switch stack. Now that also extends to, let's say you've got 5 or 6 switches, they're all discrete, they're not stacked. So stacking in Cisco terms and in Juniper terms and in most vendors' terms is a specific term that basically means logically combining switches into a single device for management purposes. Now, if you've got 6 switches and they're all running as a single network, a single VLAN, which is a single layer 2 construct, then essentially they provide a single broadcast domain. That is to say, at layer 3, a broadcast packet from device A will be picked up by the 56 other devices on that network. But each device will only collide, if it does collide at all, with its own traffic, which of course by design they're not going to do. So essentially saying many collision domains or saying that there's one collision domain per device basically is the same as saying that collisions are no longer something you need to worry about.
And have we covered the difference between a broadcast and a collision domain?
Not really, no. So a broadcast domain is essentially the group of computers which, when a certain type of IP packet is sent, that is a packet sent to a specific address that all devices listen to, will all receive jointly and severally. So if you've got a network at home, you might have 192.168.1.0 as your network. You might have 192.168.1.1 as your router address, your gateway address, and you might have up to 253 other devices on that network, including your own PC, of course. Now, if you craft a packet, say a ping, that goes to 192.168.1.255 in that construct, you're actually pinging a broadcast IP address. You're pinging an address that every device on that network will be listening to at all times by definition and by design. That makes that network a broadcast network. Now, while I've just talked in terms of layer 3, it actually exists at layer 2. So there are specific MAC addresses, which is a layer 2 physical address between devices that you can and do use to communicate between devices. Now, if you use the broadcast address of all ones, essentially in binary, that is FF, 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 FF in hexadecimal, then every device on that network is going to receive it at the same time. That's a broadcast domain. Now, collision domain I've touched on quite a bit already, but essentially it consists of the ability or not of 2 devices on the same network to talk at the same time and have their message heard by whichever device it is that intends to receive that traffic. So a switch allows that to occur, and therefore there's a collision domain per device, which is the same as having your own highway from your home with no one else on it. You can't exactly run into anybody if there's no one there, versus a hub where it might be, I don't know, Parramatta Road on a busy day if you live in Sydney, where there's hundreds of cars, hundreds of other vehicles, plenty of opportunities to get yourself in trouble, as it were.
Excellent. I've got a stack of questions. We'll ask a couple more, then I think we should move on. It's already 8:30.
Yeah, sure.
Is a load balancer a kind of switch?
Yes and no. Load balancers are actually sort of more of a layer 4 device in most terms. So load balancers will typically be used to interrogate layer 4 through 7, that is the application stack down to TCP, to identify where to send traffic. Now they also do a lot with, well, a good load balancer at least will do a lot with business logic as well, and therefore can, potentially steer the traffic based on whether it's, if it's a website looking for an image versus looking for a bit of, scripted website information or what have you. Now, Amazon Web Services, for example, have multiple types of load balancer, and they do have something called a network load balancer, an NLB, which has none of the business logic of an application load balancer, but has much, much more performance as a result. Now, it kind of sort of mostly works at layer 3. I say kind of sort of mostly because while it relies on TCP to do what it does, relies on IP to do what it does, and will transport either TCP or UDP, both of which live above layer 3. It also does have a bunch of health-based or status-based checks that it does that can live it up to layer 7. Now, load balancing, though, can exist at layer 2 and 3. And in fact, there's multiple ways to aggregate links that we'll talk about in subsequent weeks that do provide some forms of load balancing, as it were.
I think one last question. If bridges and hubs are obsolete, why do we still teach about it?
One, because, as I said, hubs, any switch can become a hub if you mistreat it. And understanding how a hub behaves is important to understanding how to troubleshoot a misbehaving switch. I've lost count in my career of the number of times where we've seen performance issues on a network, and it's basically come down to a switch that's now no longer doing its job of keeping collision domains separate and is now resulting in devices that simply can't talk to each other. Bridges, as I said, the term bridges is now used interchangeably, and in the standards, be it spanning tree, trill, or similar, you'll see references to bridges. You won't necessarily see references to switches. So it's best to understand that when we're talking bridges, we're talking switches.
Okay, let's go on. We've still got
Cool.
piles of questions. They can wait.
Yep, no problem. So now we talk about the media. So we've talked about the types of devices, switches, routers, hubs, etc. But obviously, many of you will be familiar with at least some of the forms of media, that is connectivity, that these devices can use to talk to each other. You don't need a lot of this knowledge for any of the associate level exams, but you do need to have a basic grasp on the fact that there are multiple different types. Typically, in a typical enterprise network, the two types you're going to see the most of are copper. So that's your typical eight core twisted pair cable that you probably have got into the back of your computer if you're not connected via wireless. Or there's fiber optic cables. Now, there are a couple of different formats for fiber optic. There's single mode, there's multi-mode. You don't need to know a lot about those for the routing and switching associate level exams, other than to know that there are different types. And, fundamentally, you can't use one type where another is required from a standard point of view. What you do need to know is that for both types, there are essentially two types of cabling, be it electrical or optical connectivity. So there's what's called a crossover cable, which connects the transmit side of a cable to the receive side of a device and vice versa on the other end, or there's straight through, which connects, line A to line A, line B to line B, line C to line C. Now, these days with your modern switching, the difference between a crossover and a straight through is negligible because pretty much every modern switch, at least on the copper side of the fence, will auto sense, and if you've used the wrong sort of cable or if it's connected to a device that requires a reversed connection, it'll do that for you. So you don't need to worry about it so much, but it is still in the standards because you still do get devices out there that require either a crossover or a straight through connection. And now when this is required, it will typically be disclosed in the operating guide or the manual for that device in question. But generally, modern computers, modern switches, they'll cope with copper connections that are either crossover or straight through. Now, with fiber, it's always going to be a crossover connection. And in fact, the one thing I would say, it's not in the exam, but it is a piece of sage advice that I've learned from many years of working with fiber. If you plug in a fiber connection and it doesn't work, flip it over and plug it in again, because 9 times out of 10, that's the problem. What you've essentially done is connect transmit to transmit. And what you need to do is make sure it's connected transmit to receive. In the exam, you do need to know the difference between copper and fiber. That is to say, you could in some of the exams see a photo of a particular connection type, and you need to be able to identify what sort of connection it is, whether it's a copper connector or a fiber connector, for example. Now, in any case, and this is particularly important with fiber because like any good standard, there are hundreds to choose from. And unfortunately, fiber has sort of seen a lot of standard sprawl, as it were. You've got to make sure that the interface, the fiber interface on one side matches the fiber interface on the other. So if you've got a long haul connection or a long range connection, say a 10 kilometer fiber optic link, you need to make sure that you're using the right kind of interfaces at both ends. That's less important with copper, where generally electrical auto sensing means that if you've, say, got a gigabit capable device and a 10 gigabit capable device and you connect them together, they'll both negotiate down to the gigabit speed. Unfortunately, with fiber, that's not the case. And with that in mind, here's a good guide that will get you through the exams, no problems. Generally speaking, in the enterprise space, you don't need to worry about setting speeds. And in fact, it's generally best not to. If you plug in a device, the first thing it'll do is figure out what the switch that it's connected to is capable of, and they'll both settle on the fastest speed that both of them support. Now, that can be different in service provider land, where sometimes you do need to force set an interface to a particular speed or it won't work. But if you do force set a speed, then sometimes it won't work in the enterprise. So generally speaking, unless you're told to reconfigure a device, it's safe to assume you don't need to. Now, duplex-wise, I've already touched on duplex. Essentially, duplex talks about the ability of a device to both transmit and receive at the same time. Essentially, 2 separate channels of communication, one in and one out. These days, particularly with switching, you'd almost always use full duplex. That is to say, it can talk at the same time as the remote device can send traffic to you. Computers are fast enough to cope with that, and networking equipment is certainly designed with that in mind. Now, if you do happen to, and this is something that is generally automatically set as well, particularly at the higher speeds. If, however, you do manually set duplex and forget to manually set the remote side as well to the same setting, the best outcome you can hope for is poor performance. The worst outcome you can see is no performance, no network link at all. So generally speaking, what you're looking to do in an enterprise environment is leave things as they are, but the exams do ask, for example, what happens when you misconfigure duplex. And as I said, the best case is you get poor performance. That is to say, one side thinks it can talk at the same time as receive and the other side can't. and you end up with collisions. And they typically happen at the full duplex end. They actually come up as interface errors when you're running troubleshooting commands. Or the worst case is the link just does not come up at all. In terms of connection types, copper, there's really only one. There's the standard RJ45 connection these days. Yes, there are others, but generally the only one that you're going to come across in an enterprise environment is the standard RJ45 8P 8C connector, which basically looks like an old style telephone jack, but a little bit broader. There's a few different types of copper cabling. There's Cat5, Cat5e, Cat6, Cat6a, etc. Broadly speaking, they're all going to do the same job. And certainly that's true for any speeds at 1000 megabits, that is 1 gigabit or lower. Beyond that, once you get up into the 10 gigabit type speeds, or even 2.5 gigabit, you start to need better quality copper. And that's generally where you're going to start seeing a need for things like Category 6 cabling. But broadly speaking, there really is only one type that you need to worry about. That's not true in the fiber space. There's different types of connectors. There's different types of optical wavelength. There's near infrared and far infrared that are used. Carriers might use 64 different wavelengths all at once or more. And as I said earlier, the biggest issue that I've ever seen, assuming you're using the right connectors and the right types of interfaces, is a flipped cable. That is to say, transmit at one end is connected to transmit at the other, rather than being connected to receive. Real simple fix, just unplug a cable and turn it over, which fortunately with fiber is relatively easy to do. Once we get into the chassis type environments though, and by chassis I mean anything bigger than what I'm going to call a pizza box device. A pizza box device looks like a pizza box, so it would typically have up to 48 switch ports on the front of it. Whereas a chassis device will typically look like a small bar fridge, or even a very large bar fridge if you work in a sufficiently large environment. With those, obviously, we get a lot more complexity, but fortunately, in the associate level exams and in Networking Plus or Network Plus, you don't need to worry about those. It's really just focused on the basics of network troubleshooting at that layer 1 and 2 level. Now, what does hardware do in all of this? So first and foremost, switches create collision domains. You've got one per device, one per switch port, whereas routers create broadcast domains. So a broadcast domain, again, separates devices essentially at layer 3, whereas a collision domain separates them essentially at layer 1. Now, there's a bit of a gray area. Collision domains rely a little bit on layer 2 to enforce, and broadcast domains do work at layer 2 as well. But for the purposes of the exam material, that's the way to look at it. Before I move on to collision domains in a bit more depth, any questions worth answering? Or
Oof,
that we
that's
need
a
to
loaded
answer?
question, isn't it?
Yeah. Well, they're all worth answering, yes. Any questions that I need to answer, I guess, is a better
Uh,
way of putting it.
Here's an interesting one. I'm just looking for some. There are quite a few questions here. Are all hubs, bridges, routers, etc., are they all active devices that require power, or can we build a passive version to save power?
Um, Look, broadly speaking, yes, they all do require power. These days, these days you're not going to see a hub all that often, and I have heard of hubs that are low power enough that they will essentially use, stray power off the device. But these days, that's really not a concern. A modern switch will typically use on the order of 1 or 2 watts per port. So, that's a reasonable amount of power. Yes, you could theoretically use power over Ethernet to drive it. And indeed, for small edge devices, say 12-port desktop switches in an enterprise environment, you absolutely can power them off, power over Ethernet. So you don't need to have a wall wart plugged into them as well. But yeah, generally speaking, they're all power hungry enough that that they do need power. And that's certainly true for particularly enterprise grade routers, or service provider grade routers. Some of those will use many kilowatts of power just to keep the lights on, as it were.
Is SD-WAN covered as part of CCNA?
No, it is not.
Great. Dennis is saying, for clarity, you're saying that copper cables, like Ethernet cables, that really doesn't matter what kind of cable it is, crossover straight, but for fiber it matters, right?
Yes, more or less. So for Ethernet these days, or for copper Ethernet, to be very clear, because Ethernet doesn't actually in itself strictly define the physical medium on which it's carried. So Ethernet's just as happy on fiber as it is on copper. But for copper Ethernet, um, you do generally, well, you did generally need to concern yourself with crossover versus straight through. But modern switches, so pretty much anything built in the last 10 plus years, will have an auto sense capability. So they'll be able to identify what the remote device is expecting from it, and they will adjust the port accordingly, and they'll just use electrical signals to figure that out. For fiber, it absolutely matters because you only have two optical lenses on the front of each what's called an SFP, or each optical interface. One side is transmit and one side is receive. Now, a fiber optic cable is literally just two pieces of glass that are essentially strung like spaghetti next to each other. And you can't have transmit talk to transmit. And of course, there is no way, unlike in an electrical world, there is no way for the device to figure out what you've done and to flip transmit and receive. So you essentially have to do that for you. There is no such thing, such as it is, as a crossover cable in the fiber optic world or a straight through cable. There are just cables. And if you plug it in and it doesn't work, the best thing to do is unplug one end and turn it over. Because chances are it's just simply crossed transmit and receive over.
Okay. Can a PC tell if it is connected to a hub or a switch, i.e. if somebody was using a hub for snooping?
Yes, it can. Yes, it can. So the simple thing to look for, and I am generalizing a little bit here, but the simple thing to look for is whether the uh, PC has negotiated to half duplex. If it's negotiated to half duplex, that means you're connected to a device that has a collision domain that is bigger than just that device. So it has fewer collision domains across the board. That in turn means that any traffic that is sent by that device is going to be picked up by anything else. However, that's not a common way to intercept traffic. We will talk in future weeks about what are called span ports, switch port analyzer ports. And pretty much any modern switch these days allows you to tap traffic from another switch port and listen to that passively. So essentially send that traffic to a traffic analyzer or what have you for further investigation. Now, when that happens, you can't tell. It's not something that the PC can easily pick up on.
Okay, two last quick questions about cables. You were talking about fiber optics and switching and stuff before. What about a half duplex single fiber optic cable? Is such a thing?
So there are fiber optic cables which are a single strand. So you could call them a half duplex cable. It wouldn't actually be quite accurate. The way those typically work, and they're very common in service provider land. If you're in Australia and you're connected via fiber to the NBN network, then at some point in your network and possibly from your network termination device on the wall, there'll only be a single strand of fiber from there to where it goes next, which is, typically an exchange or similar. Now, the way they work, the problem with light is that if you use the same frequency, the same wavelength of light in both directions, then you get collisions. You get basically standing waves. You get the two devices at each end being blinded from each other. So the way that such devices, they're called BX optics, bidirectional optics, work, is they'll have one wavelength for transmit on one side and one wavelength for receive on that same side. So wavelength A and wavelength B on one side, and wavelength B and wavelength A on the other side for the reverse. So essentially, the challenge there is then instead of simply flipping a cable, you then need to keep track of what kind of optic you're running where, and are you running an uplink or a downlink at each end of the link? Because that will affect what wavelengths of light you've got to provision for on the network. So yes, in short, it is possible to have a single strand of fiber, but it's not really half duplex. It's still full duplex. It just uses light to separate the wavelengths rather than or wavelengths, sorry, to separate the traffic flows rather than physical strands.
And what's the difference between Cat5 and Cat6?
Biggest difference is the number of twists in the cable. So in order to ensure no electrical interference, the cabling uses a fairly tightly regulated set of twists on a pair basis. So you might hear cabling referred to as UTP or STP. That means unshielded or shielded twisted pair. Basically, it means out of the 8 cores or 8 pieces of copper in that cable, they're arranged into 4 pairs. Each pair is twisted around itself at a particular rate per 10 centimeters. With Cat6, the cabling grade tends to be higher, so the copper tends to be a little bit heavier. If it's shielded, the shielding will be a little bit better, but the cabling also has a higher twist rate in it. The long and the short of it is that Cat6 has to be able to sustain a much higher data rate. That is to say, a much higher signal speed than a Cat5 cable has to cope with. So Cat5 and Cat5e are generally okay up to about a gigabit per second. If you want to run 10 gig per second over Cat5, you're going to be running it over very short lengths. Whereas Cat6 and Cat6a, which is the sort of the enhanced version of Cat6, if you will typically run to much longer lengths before 10 gigabit Ethernet's going to have a problem.
Okay, we're rapidly running out of time.
Yep, no problem. Let's keep churning. So, all right, so collision domains, we have already covered this a little bit, but essentially, again, to recap, collision domains, any devices that see each other or can see each other's traffic can potentially collide with each other. Now, that's particularly true if they can't talk at the same time. The human analog would be if you're in a room that's got lots and lots and lots of people in it, you eventually reach a point where you can't hear the person standing closest to you, no matter how loud you talk, because of the sheer amount of noise around you. Now, to everyone else, that's not noise, or to each individual, the words they're producing aren't noise because they contain a message they're interested in, but to you, they're certainly noise. That's essentially what a collision is. It's where two devices are trying to talk at the same time and in doing so, prevent either of them being heard. So a hub is just one big collision domain. If you've got an 8-port hub and you've got 8 devices connected to it, they're all capable of hearing all of the traffic, they all send all of the time, and they're all capable of basically preventing all of the others from talking. Now, there's a whole bunch of mechanisms that Ethernet use to try to enforce fairness. But again, you get to about 30 devices, those mechanisms fall over pretty quickly. Switches, if the switch is working properly, you've got one collision domain per port. So each device can only collide with itself, and obviously that's not something that has any meaningful chance of happening. Broadcast domains. So with broadcast domains, similar concept, but at a slightly higher level. Essentially, instead of hearing every conversation that happens in an area, they'll only hear the traffic that is intended to be heard by everybody. So they do require layer 3 functionality, but they do use layer 2 to work. And generally speaking, switches, and I say generally speaking because there is an exception called the VLAN. One switch will equal one broadcast domain. So if you've got 40 devices on a single switch and you send a packet to the broadcast address, all 40 devices are going to receive that and do whatever they will with it. Now, routers break up broadcast domains. So a router will typically have a broadcast domain on one side and a broadcast domain on another. Very loosely speaking, if you've got an internet router at home, which you do, you'll have a broadcast domain on the inside of your network on the LAN. That's the side your PC is connected to. And you'll have a broadcast domain of sorts on the service provider side on the WAN. Now, I say of sorts because there are some nuances here that are outside the scope of this course. Now, why do we care? Collision domains, I've said that already, the smaller you can make them, the more of them you can have, the better for performance. The fewer times devices have to retransmit because something else shouted them down, the better. And broadcast domains, again, the smaller they are, the more efficiently your network can run. That's particularly true with some applications. Microsoft Windows used to be very sinful in this regard. Use a lot of broadcast traffic where other forms of traffic would have been more efficient. Any questions?
Are we nearly at the end?
We are getting pretty close, yeah. But we can keep going if you like.
I reckon keep going. We've got a pile of questions, but I think
Yeah,
we
sure. No
have one
worries.
big session at the end now.
Yep, perfect. Okay, so protocols and ports in the exam. We've covered a little bit of this already, so I will skim it somewhat. But long and the short of it is, most of the exams focus on the TCP networking layer. Associate level really focuses on this because that's what the vast majority of the world uses. IP is your layer 3, TCP and your UDP are your layer 4. And I've already explained that TCP provides a lot of error correction, whereas UDP basically provides a best effort service. So TCP looks like this. You will have these slides, and certainly if you're doing the exam, it's worth understanding how this goes together. The key parts are there's a source port and a destination port. You can think of them as channels to identify where and how traffic flows. UDP, on the other hand, much simpler. There's a lot less in the header of the packet because really it doesn't care about things like um, uh, reliability as such. So essentially all it cares about is how big's the packet, i.e. what's its length, and what's the checksum of the data inside the packet, which gives you some form of error correction, as it were. Ports. So 3 different packets have come in, which goes where? And so ports essentially are used to help define, is it TCP, is it UDP? That's the first test that gets done. Okay, it's TCP, it's UDP. Essentially, those ports are used to help identify which traffic flow goes to which application. So if nothing else, they're a signal to the kernel or the application that that a particular flow or traffic flow is for them. Some common ports that you do need to know for pretty much all of the exams. Obviously, some common ones there that you might be familiar with. Port 80, for example, which is HTTP. Port 443, which is used for HTTPS or secure sockets layer. Yeah, so well worth understanding these because you can expect questions in the exams about this.
Just a quick interruption. We're going to
Sure,
close the Q&A in 5 minutes. So if anybody's
sure.
got questions, bung them in there now.
Yep, sounds good. So we've touched on the three-way handshake as well. Essentially, it's a mechanism for TCP to guarantee that 2 devices can in fact establish a connection. And essentially, you can think of it as, hello, are you there? Then yes, I am. Are you there? And then yes, I am as the third response. So it's SYN-ACK, and ACK. So that allows the 2 devices to confirm each other's existence with basically 3 packets, and that is called the 3-way handshake. Has a similar way to finish, which is thank you, I've received everything, goodbye. Thank you, goodbye, goodbye. So if you think about the way a lot of people finish a phone conversation, it's a very similar set of conversations. And again, it helps guarantee that both devices have a complete understanding of where things are at. But to the point Shane raised earlier, it is very, very, very inefficient compared to UDP in particular. Now, TCP IP addressing, you're going to need to learn it. And yes, we all get it wrong, myself included. It is very binary heavy, and we just do not have the time to walk through the examples in any length. But I do strongly encourage you to read these slides, including the supplementary slides at the end of the deck. So it's all binary. It's all based in IPv4 on a 32-bit address. And basically, the addressing that you typically are going to see in a service provider environment is what's called RFC 1918. RFC is a request for comments. It's call it an internet standard, if you will. It essentially describes mutually agreeable norms between, internet participants. And everyone on the internet has essentially agreed that these three ranges of networks will never be used on the internet, which means you can use them at home. If you're using anything that's not these at home, then you're very potentially preventing yourself from accessing other parts of the internet. Hopefully, you're not affecting anyone else, certainly if your service provider is doing their job right. There's two parts to it. There's the host and there's the network. I've already touched on this earlier, but essentially the host part is the last octet, the 33, whereas the network part is the first three octets. So some examples. If it's confusing, go through the tail end of this deck, the supporting material, because it is complicated and it does take some time to get around. Some of the basic subnetting examples, /24, for example, are fairly easy because they do line up neatly with the 4-octet range. But then you get things like a /27, which allows you to have lots more networks in a given space, but comes with the trade-off of having to understand where your networks start and stop, as it were. IPv6, similar deal, but everything's 4 times bigger. So 128-bit addresses, which gives you lots and lots more hosts. If you basically wanted to give every IP address, every device in your home an IP address, you absolutely could with IPv6 with heaps left over. Makes it a lot easier. There's a lot of capabilities that it has that IPv4 just was never built with. It comes, for example, with IPsec, that's IP security, as a core part of its standard. Much better way of doing things, but comes with a whole bunch of additional learning. And increasingly, all of the exams focus on IPv6 as well. So there's a good example of an IPv6 address. Gets pretty ugly pretty quickly, and you do end up with lots of zeros in them because obviously with, ridiculously large numbers of hosts, you're going to have a lot of empty space. But there are some ways you can simplify this. So you can strip out early zeros, so that 0388 becomes 388, for example. And then if you've got, groups of zeros, you can actually get rid of them at least once. So for example, in this case, we can take that previous example, which is not the easiest thing to type in the world, and turn it into something that's a little bit simpler to type. But of course, it's even better than that because if you're using IPv6 correctly, you should never need to type an IPv6 address because devices have this concept called stateless auto configuration, which allows them to identify what their IP address is, their IPv6 address is, without needing anything on the network to tell them. And that includes not needing a DHCP server. IPv6, much like IPv4, but there's no such thing as a broadcast address. So everything that I talked about with broadcast earlier does not apply to IPv6. It has different ways to allow a device to talk to multiple devices in the network. IPv6 also has what's called SLAC, Stateless Address Auto Configuration. And essentially what it involves is an IPv6 router telling everybody around that it is an IPv6 router using what's called a route advertisement or an RA. And then devices respond to that by going, okay, cool. Now that I know what your address is, I'll create my own and make sure that it doesn't conflict with anybody else's. And essentially it just uses a MAC address, its local layer 2 address to do that. Now, what are we going to cover next week? We're going to cover switching, we're going to cover VLANs, we're going to cover spanning tree, and we're going to go into a little bit of detail about the layer 2 Ethernet frames and so on. So filling in a few of the gaps from today, I guess, is a fair way of putting it.
Sounds
Any
like a lot of
questions?
fun. Oh, yes, we got questions. We've got questions.
Excellent.
What's a good trick to confirm which layer an issue is seen at, especially if it's TCP or application layer?
That's an excellent question. The best advice I give anybody and everybody, and having run operational teams, so I've given this to my own staff members as well, is always start from the bottom up. Always start from layer 1 and work upwards until you've identified the problem, because it's almost always at a lower layer than you think.
Okay. At which layer are ports defined?
Ports are defined at the IP layer, but take weight at the TCP layer. Now, the reason I say that is that at the IP layer, there is the concept of ports and protocols, but TCP and UDP extend that by having their own header constructs for ports.
Hey, what's the maximum length for fiber cables? We know LAN's Ethernet shouldn't be longer than 100 meters.
So typically, I'm going to use my favorite phrase, it depends. But typically, in a typical enterprise environment, you would typically see LR optics, so might be 10G base LR, for example, long range, which is typically designed to cope with links up to 10 kilometers. Now, in service provider land, you might see that extend out to 40 kilometers, or even 120 kilometers with sufficient optical power.
Okay. Where are we here? Why does a loopback network / IP required on an endpoint? Not sure that that's
So loopbacks are typically not required on endpoints. They will have their own link local address, particularly in IPv6, or they'll have a local host address of universally defined as 127.0.0.1. Now, typically those addresses, the local host addresses, are typically used for kernel level communications. So essentially for the device to talk to itself. Loopbacks are typically only seen commonly in routers and switches, and they're typically used as a mechanism for that device to essentially announce itself to the world. So where a link local or a local host address is used for a device to talk to itself, a loopback address is used to identify a device to other hosts on the network.
What are the key advantages of using a layer 3 switch over a router? Or are there any?
So there's advantages and disadvantages both ways. Typically, a multi-layer switch or a layer 3 switch will have more ports, obviously. It'll typically be cheaper per port, but it will also tend to have lower levels of scale. So a multi-layer switch is typically great in a enterprise network, for example, where you might have, worst case, maybe a few tens of thousands of devices all connected together at layer 2 and layer 3. Whereas a router, particularly in, again, that sort of enterprise space, would typically be capable of talking to the entire internet in terms of layer 3 routing. But again, that comes at a cost. The per port cost of a pure router is generally much higher than a switch.
Okay, in today's advanced networking, why would you use a router for routing rather than just a physical firewall that can do both routing and protection?
Performance mostly. Firewalls do have a certain amount of overheads associated with being a firewall. They've got to do traffic inspection. They've got to do all sorts of other things. They might have to do network address translation, for example. And absolutely, you can use a firewall as a router. Many people do. But where routers really come into their own, again, particularly in the enterprise space, particularly, well, absolutely, especially for service providers, is raw packet performance. They don't bother doing any traffic inspection. They don't really care if they're carrying malicious traffic or not. It's not their job to worry about that. But as a result, they can get speeds that are, an order of magnitude higher than an equivalently priced firewall.
Okay, we're down to the last three questions because I think there were piles more questions there, everybody. So apologies if we haven't got to your ones. We've tried to get to as many as we can. We will have answered over 40 something questions tonight. We've had about 70 or 80, and that's quite a lot for a session like this. But these are the last three. The rest, I would encourage you to bung into the forums because I think you can bring it into a more detailed discussion there too.
Yeah.
How do you get a DHCP response for a new IP device?
So first of all, you need a DHCP server. The device, when it connects, will basically send out a packet, a broadcast packet as it happens, asking for a response from a DHCP server that basically tells it what its network needs to be. So that broadcast packet is very specially constructed because at this point that device has no concept of what network it's connected to or what have you. The DHCP server will also respond with a broadcast packet at that point, because again, the client doesn't have an IP address at this point. So the only thing it can receive is a broadcast packet with some details saying, okay, you say this is your MAC address, here's your IP address, here's the gateway address, and so on. That device will turn around and say, okay, I'm accepting that offer, or I'm saying I want that. And then that DHCP server will, in a fourth response, say, sure, here you go. I've confirmed this is your address now, as it were.
Okay. Which is more secure, TCP 433 or port 80?
Well, all else being equal, and assuming you're using SSL correctly, then TCP 443 is always going to be more secure than port 80 for the same traffic and the same web server application.
What effect does the material used to make the core of the cable have on the speed of signal transmission, e.g. copper versus aluminium? I didn't know that people used aluminium.
That is an excellent question, and yes, they do. There are different propagation qualities for each. I can't remember off the top of my hand which is quicker, but fundamentally, for the purposes of dealing with anything up to, well, even 10 gigabit Ethernet, it really doesn't matter because it's not propagation speed you're after so much. Once you're dealing with speeds above a gigabit, you're dealing with the skin effect, and you're actually using the wires as a wire guide anyway. So you're actually transmitting an RF signal rather than an electrical signal. So generally speaking, from that point of view, the choice of material doesn't much matter. Yes, there is a difference in propagation speed, but even at the speeds of 10 gigabits per second, which is realistically all you can get out of a copper connection meaningfully, you're not going to notice the difference.
Excellent. Well, on that note, I think we're done for this evening. We do try and keep these to less than an hour and three quarters, nominally an hour and a half, about an hour of work and half an hour of questions. I have noticed in the chat that somebody's got a drinking game going on for every time you say it depends.
Well, it's the same in my in my regular lectures as well, so that's okay. They'd better have a nice big bottle.
Absolutely. And thank you so much. It was a really good session. In fact, Kit has been saying to me in the background that she's now interested in networking, which I think is quite a shock for her. And so really well done. Thank you so much to everybody for coming along. We've had a huge attendance tonight and it's been a really good session. We really look forward to having you back next week, same bat time, same bat channel, with I think Jack as your host next week, but Iain as your mentor as always. Thanks, Iain. It was great.
Thank you very much for your time, everybody. Have a great evening or day, depending on where you are in the world.
Yes, and big thanks to Kit as well for keeping us all in line. Good evening.